To understand how your laptop at home talks to Google's servers in a galaxy far, far away, you first need to understand how your laptop at home, or in a data center, talks to another computer located in the same physical location. To do that, all the computers must be connected in some way so that they can transfer signals to each other. Let's assume that we're only interested in wired connections at the moment. One way to connect computers to each other is give all computers a direct connection. So let's say we have two computers, computer A and computer B. Now let's assume that we can connect these two computers over a wire and they can communicate with each other over electrical signals. In practice, this cable is called Ethernet. Now let's say we have three computers. How do we connect these computers together? We do the same thing, except now we'll have an Ethernet cable going from computer A to computer C and computer B to computer C. Now data can transfer in both directions, from A to C and from C to A. Now, this seems like a pretty good model, but what happens if I have 100 computers? To connect 100 computers together, I would have to have computer A connect to computer B, connect to computer C, connect to computer D, connect to computer E. As you can see, this is going to get pretty hairy. There's going to be a lot of wires and a lot of connections. For every computer in our 100, each computer will need to be connected to each other. So how many connections is this? Well, the first computer will have to have 99 connections to all the other computers. The second computer will have to have 98. The third computer would have to have 97, and so on. I wonder if we can do better. One model that could prove better is using a centralized hub. All data sent by a computer is received by the hub. The hub then forwards all the data to all other computers connected to the hub. So let's see what this looks like. Say we have computer A, computer B, computer C, computer D, and computer E. Instead of creating a direct connection between every node in this network, let's have a hub. This centralized hub will connect all nodes to each other with the least amount of necessary connections. The way it does this is have all traffic flow through the hub and all nodes connected to the hub. Now, to get traffic from node A to node D, node A will send the traffic to the hub, and the hub will forward that traffic on to node D. So how many connections do we need for a 100 computer network? We only need 100 connections. That's a significant improvement from the previous model we had. This is known as the star network topology, when all computers in a network are connected to the central hub. One big downside of this approach, however, is each computer would be receiving data that is not intended for it. The hub doesn't yet know anything about where its incoming data should be routed to. It only knows to forward all data it receives to all other computers on the network. So this means any data that comes from node A destined for node D would go to the hub, and the hub would forward that data to all nodes in the network instead of just D. The hub doesn't know which node D is. How can we solve this problem? One way is to break down our 100 computer hub network into two 50 computer hub networks and connect that 50 computer hub networks to each other using a bridge. Now we've got two networks, network 1 and network 2.
Our goal is to be able to have computers on network 1 communicate with each other without having to take up bandwidth on network 2, and the same goes for network 2. So a bridge is slightly smarter than a hub. The hub just blindly forwards packets to computers that aren't necessarily the destination, whereas a bridge has an idea of which computers are in network 1 and which computers are in network 2. To do this, the bridge needs to know which computers are on network 1 and which computers are on network 2. It needs a forwarding table. A forwarding table will tell the bridge whether or not to forward packets from network 1 to network 2 or from network 2 to network 1. To make this possible, each computer on the network will be assigned an address. Let's say address 0, 1, 2, 3, 4, 5. In practice, these addresses are called MAC addresses. When a computer wants to send a message, it will include the address of the sender and the address of the receiver in the message. So say computer C wants to talk to computer D. Computer C will include the message as well as two important pieces of data. The first is the source MAC, and the second is the destination MAC address. When communicating from node C to node D, the source MAC will be 0 and the destination MAC will be 3. Initially, say a computer on network 1, let's say computer A, wants to communicate to a computer on network 2, let's say computer D. To do this, computer A will send its message to the hub in network 1. The hub will then forward that message to computer C, to computer B, and also the bridge. Now, the bridge doesn't know that whether to forward this message or not to network 2, and so by default, it'll forward it. It gets sent to the hub of network 2, and network 2 sends the message to computer E, computer F, and computer D to our destination address. Here's what the message looks like. Instead of source MAC 0, we have source MAC 2, and the destination is the same. One thing that the bridge does is keep track of source MAC addresses to network mappings. So say in this example, when the bridge receives source MAC 2 and destination MAC 3, it looks up in this mapping and doesn't find anything. So default will forward the message to network 2. However, after doing this, it'll add to its mapping that it had received a message from source MAC 2 from network 1. Now, say computer C wants to communicate to computer A. Computer C will create a message, and the message will have source MAC 0 and destination MAC 2. And we'll notice that the message will get sent to the hub will send it to computers C, A, and B, and will also send that message to the bridge. The bridge will notice that it already contains a mapping of destination to network of destination MAC 2. And it'll realize that this message is coming from network 1 and going to another node inside network 1. As a result, the bridge does not need to forward this message to network 2. And this is where we get our efficiency gain. Now, any computer on network 1 that wants to communicate to node A will not waste bandwidth on network 2. This is because the bridge is now aware that computer A lives on network 1. This is how a lot of networks back in the day used to be designed. But more recently, switches have replaced bridges and hubs. A packet switch acts as a hub but is able to make smarter routing decisions, which further reduces bandwidth consumption. Let's say we have a 3-node network. Computer A, computer B, and computer C, all connected via a switch. When computer A wants to talk to computer Y on the network, the switch will use the same learning protocol as the bridge, and it'll be able to eventually learn that on which port computer B lives on, which port computer A lives on and which port computer C lives on. Here are the switch's ports. When A wants to send a message to B, the switch will know where the data is coming from and which port it needs to leave to. So it will intelligently take this data from A, understand that it's destined for B, and send it only on that outgoing port for B. This means that bandwidth on the link between the switch and C is free to do other work. And this is how modern computers and servers in a data center talk to each other when they're all located in the same physical location. In the next video, we'll talk about how these computers can talk to each other when they're located on different physical locations.